sir.
Good morning, sir.
Morning, sir.
Okay, can you see my screen?
Yes, sir.
Yes, sir.
Good. Remember that. Recall that in the previous week we just talked about the history of computer evolution, how processor design has evolved over the last 50 years, starting from the first microprocessor 4004 to the latest, to the latest chips you encounter nowadays. So today, I'm going to introduce a simple yet very important concept, and this is called instruction set architecture, or ISA. And throughout the course of our computer organization architecture, we would refer to this concept, ISA, instruction set architecture, multiple times. And this is essentially an interface between, which is defined between hardware and software. Okay, so recall that if you are entrusted with the task of building a computing system, and you appreciate that today's computer systems are very complex, comprises billions of transistors. So given such a task, so you might wonder, so where should you start from? So that is a fundamental question of designing a very large system. So what are the design issues? What are the factors you need to consider? And first of all, from where you should start? How would you decompose the problem into smaller components so that you can solve one of them one by one? So these are the issues you need to consider when you are given the task of designing a very complex machine like a 2-disk processor. We talked about technology scaling. Remember, we discussed Moore's law. Can somebody restate this law?
The technological advancement doubles every 18 months or
Right.
12 months.
Good. So this is some kind of empirical projection that the way our technological research has been advancing, so it has an immediate impact on technology scaling. Now, when you say technology scaling, it means that given a silicon chip on which the processor would be built, you can accommodate more and more transistors. That means bigger and bigger circuits can be accommodated on a small chip. And this is referred to what is called the technology scaling. So with time, we have observed that there is a tremendous and exponential sort of technology scaling, which is captured in this empirical law, Moore's law, which was given by Gordon Moore, one of the Intel founders. And as you can see that if you just look into the last 50 years or 5 decades of computer revolution, so this is the first microprocessor which was built in 1970, 50 years ago. And you can see the picture of the chip here. And this comprises around 2,000 transistors. So today, you have this kind of processor in 2020, and the chip comprises 4 billion transistors. So this is an example of technology scaling. So you might wonder that if you are asked to design a processor with 4 billion transistors, how to handle such a large and complex design? So one thing obviously is the technology has advanced so far. Memory technology has advanced, logic design technology has advanced, the semiconductor fabrication procedures have advanced, and so on. But even then, given 4 billion transistors or a very large number like that, how do I represent such kind of design? And because it involves a lot of optimization problems, right? In order to make a compact design, you have to take care of the placement of these transistors, the interconnecting those transistors. You need to address the power issues and so on. So how do I handle such big design? Obviously, you need computer-aided design, right? Because it's not possible to design such handle the design of such a large system using manual system. So you need basically computer-aided design tools. So what happens that you use the previous computer to design the new generation of computer, and that's what is called the bootstrapping. So what I'm meaning, what the message I want to pass on to you is the following: that this exponential scale which is being experienced over the last 50 years is due to the result of a virtuous cycle, where the computers which are available nowadays, the power of those computers is used to design the next generation of computers and so on. So that means we have the computer-aided design tools or software tools, and these tools are being bootstrapped in every generation. Okay, meaning that when you are going to design the next generation of computer, you can use the power of this 2020 computer and the power of the most recent computer-aided design tool, electronic design automation tools, to handle the design of the next generation of computers and so on. So that's how the technology scaling has been implemented because of this continuous bootstrapping, which has been possible because of the arrival of newer generations of computers, and those are being used to generate the future generations and so on. You got the idea, right? Well, now let us look into a computing system hierarchy. So if you consider hardware as a black box, so what does it contain? This slide we discussed in the previous class, I want to just go through it very quickly. So at the core of it, you have the what is called the bare machine, which is nothing but a collection of logic circuits. So it has combinational circuits, sequential circuits, different flip-flops representing states and so on. So it can, since it is just a collection of logic circuit, obviously it can communicate to the external world through sequence of zeros and one, right? So it can understand only binary strings, and this is called machine language. All right, so basically these are nothing but electrical off and on signals. So given this, which is the bare machine, so you have this can understand a sequence of zeros and one, but as you know that handling sequences of zeros and one is cumbersome. So instead of representing those sequences or binary strings, what we do, we use some kind of mnemonics or assembly language, like add, move, load, and so on. And this collection of assembly language, which is essentially has one-to-one correspondence to this machine language instruction, this collection of assembly language set is called instruction set architecture, or ISA. Meaning that suppose you have already designed this bare machine. So this machine is supposed to understand, or machine is supposed to perform certain operation. And those operations you designate using some kind of mnemonics or assembly language. So that means the machine is now equipped with a set of assembly language instructions. In other words, if you write a program using that assembly language, this bare machine would be able to execute those instructions one after another. So what is meant by the instruction set architecture? It is the behavior of the machine as apparent through the instruction set. So the behavior of machine, as we know, that it can also be represented in terms of the interconnection of logic gates. But that representation would be further down. So we don't want to look into those details at this moment. We are going to represent the behavior of the machine in terms of the power of instruction set it possesses. All right. So that means I design a machine and I say that, well, these are the instruction sets which will be supported by this machine. The attributes of the instruction set, or the collection of the assembly language instruction set, globally defined what is called the instruction set architecture. And you can also appreciate that this, if you look into this envelope, So this is the envelope which lies at the interface of hardware and software. Why? Because at the inner circle you have this bare machine or the pure hardware, and once you have the power of instruction set or assembly language instruction set, you can write further programs using that assembly language. For example, you can build your compiler operating system using this assembly language and so on. So this boundary actually defines, this is the boundary which defines the hardware software interface. All right. So above this, you can write an assembler so that those assembly language instructions can be automatically translated into machine language, the strings of zeros and one. And this interface can directly understand machine language, for example, add CAB, this kind of strings. And the assembler would translate them into binary bits or binary program, which will be executed by the bare machine. And above that, you can design compilers, operating systems, and so on. If it is equipped with a compiler, then an external programmer can interact with it using high-level programming language, and so on. And beyond that, you write application programs and so on. So this is the overall computing system hierarchy. At the inner core, you have the bare machine, which is pure hardware, collection of electrical circuits. And then you are going to envelop the machine with different layers. The innermost layer is the bare machine. The next layer is the instruction set architecture. That means covering the machine with the collection of assembly language instruction set and so on. Is there any question at this moment? So this gap is called the semantic gap of the machine, because from the external world, you interact with the machine using high-level language. The machine can understand only sequence of zeros and one or instruction level. So this is the level of understanding of the machine, and this is the level of understanding of human. So the gap, this conceptual gap is called the semantic gap of the machine. So as you can see that the red ellipse denote this hardware-software interface, because beyond this, you have this bare machine equipped with this assembly language set or machine language set, and on the top of it, you have other layers, other software layers. So this is the so-called hardware-software interface, which is very important from computer architecture perspective. So let us look into the bare machine. So this gentleman represents the strong. He has to be very strong because he represents the entire hardware structure. So on this hardware structure, it supports the platform, which is called the instruction set architecture. So what is instruction set architecture? It's the collection of the assembly language instruction set supported by the hardware which you have already designed. Right? And so this defines the hardware-software interface. And once the assembly language instruction set or the instruction set architecture is defined, then the software engineers can play with on the top of it. Using this assembly language instruction set, you can keep on developing other upper layer softwares. So this is the definition. So this is the interface. The collection of the assembly language set lies at the interface of hardware and software, and that defines the instruction set architecture. So from the instruction set architecture, suppose you are at this level at instruction set architecture. If we look down, you would see the complexity of the hardware. If you look at the top, you would see the complexity of software. So you can formally define the instruction set architecture as follows. It is the collective attributes of machine language instruction set defining the hardware-software interface. Does it make sense to you? In other words, given a processor, looking into from purely hardware perspective, the processor is supposed to perform certain basic operations, right? The collection of those basic operations is called the instruction set architecture, because these are the instructions or basic fundamental instructions which the hardware machine is capable of executing. All right. So in fact, when you study computer organization architecture, we would essentially start from the designing the instruction set architecture first, and then we will design the hardware below and the software above it. Now let us look at the hardware hierarchy. In the bare machine, we said that it's a collection of circuit, combinational and logic circuits, and sequential finite state machines. All right. So at the base level, you have just transistors, which are nothing but semiconductor switches. And interconnection of transistors, by interconnecting several transistors suitably you can form different kinds of gates, logic gates, or logic elements. And interconnecting logic elements, you can construct flip-flops and so on. So at the bottommost layer, you have the transistors. These are the basic electrical elements, which are nothing but semiconductor switches. And they can have two states, either 0 or 1, or on or off, something like that. Using interconnection of these transistors, you create logic gates, which you are familiar with. And we have names for that, like AND, OR, NAND, etc., and so on. And then you design the flip-flops, interconnecting flip-flops, you design your shift registers and so on, and other complex logic circuits, sequential logic circuits, finite state machines, and so on. So that's why in the hardware also you have several layers of hierarchy, as you can see. And once you have these flip-flops, logical memory, registers, logic gates, and so on, you can build the other complex circuits. For example, a central processing unit, which comprises maybe adders, multipliers, the controller. The controller is of utmost importance in computer organization, because you have a sequence of instructions which need to be executed one after another, right? It's not that just you ask the machine to perform addition and then done. Right? Operation is not over, because you have a sequence of, when you write a high-level language program, it means that equivalently you need to perform a series of instructions at the machine level. So that means you need a controller circuit which would be responsible for executing, for picking up the correct instruction at the correct moment, and it will execute one after another. And finally, it will produce some output which will be available at the output port and so on. Okay, so from the hierarchical point of view, as you can see, you have the transistors at the very lowest level, and then you have the logical gates, and we have flip-flops, registers, and so on. Beyond that, after that, you can design the CPU, control and I/O, random access memory, and so on. And obviously, we need interconnections. You need to interconnect everything. You need I/O pads in order to communicate with to and from the external world. Obviously, you need synchronizing clock. And of course, you need electrical power and so on. So in a nutshell, so this diagram shows you the entire hardware hierarchy, which you need in order to build the inner core. Correct? Are you with me?
Yes,
sir.
Okay, so that's how we define. You have some understanding that how the bare machine would be designed. Of course, we don't. So as a computer science student, you may not be interested in knowing the physics of transistors and so on. All you need is from an abstract point of view how they function and how they can be interconnected to form the higher level of constructs. All right. So tell me, suppose you write a program in C, and which you can see this is nothing but a very simple program, and that actually performs swapping of two variables. Right? So you have two variables, V and K, and this is going to be interchanged. The content of these variables are getting interchanged. Okay. So you have written a software in program in C. Now you tell me that when you write a program like this, how it would be executed by a computer. Because as you know that computer hardware does not understand anything excepting strings of zeros and one. It comprises only gates, flip-flops, circuits, and so on. But as a software engineer, you have written a program. Now you tell me what are the basic steps that you have to go through in order to transform this small piece of software into the executable code. Because the bottom line is, you always need a basic hardware in order to execute the program, right? So what is going to happen then when you write a program in C?
So the compiler will convert it into assembly, and then the lexical analyzer and the parser, it will further convert into object modules, and then finally to binary language.
Well, partially correct, because the compiler includes your lexical and parsing. So the compiler first would analyze this piece of code, will identify which one is variable, which one is the different kinds of, whether it is an array or not, this kind of thing. And so the compiler would parse this language because using some kind of parsing rule. And so this would be at the, this piece of program would appear as input to the compiler. The compiler would translate into assembly language code, right? Of a target machine. So you have a machine in mind that this is my platform where I'm going to execute this code. And every machine might have a different kinds of assembly language set, depending on how the machine has been designed, right? So you are right that the compiler would transform in the assembly code. Now assembly code is a mnemonic kind of code, right? Symbolic language. So then it will be translated into machine code by whom?
The assembler.
By assembler. Good. So the compiler would translate into something like this. So when you would write programs in MIPS, you would encounter this kind of instructions. So for example, this is multiply immediate. This is an addition instruction. This is load word, store word, jump return, and so on. And when I say $2, it means that there is a register in hardware whose name is 2, which is identified as 2, and it means this. This tells you that, okay, pick up the content of this register and you multiply with something. It says that, well, so multiply immediate. It says that, well, pick up the content of register 5, multiply the content of the register 5 by 4, and store the result in this register. That is the meaning of this instruction. So each assembly language instruction has some meaning defined by the underlying hardware and so on. So the task of the compiler is up to this. So given the high-level language, it translates into some kind of machine language of the target machine. Next, what? Assembler. So assembler generates this binary bits. Now you please tell me. So this is a flat. This is a flat sequence of bits, right, which is stored in memory. How it would be executed by the hardware?
The controller will probably read it and then it'll issue commands.
Controller would do what?
Controller will go through this and then what do you call it? The
yes,
wires will be activated.
Correct, but see, you have to identify this is a flat string, right? So you have to identify where does it end? Where are the delimiters and so on, right? As you can see, there are so many machine instructions. So where does the first machine instruction end? Where does the second instruction would start, and so on? And after executing one instruction, what to do? When do I fetch the next instruction, and so on? So all kinds of complications are there. It's not so easy, right? Given the sequence given this machine code stored in memory, it's not so easy to execute them. Because hardware is what? You have a collection of circuits only. So that hardware has to be told, so at this time interval, at this time instant, what input string, which binary string should I feed into the input to a particular to the particular machine, and then wait for some time. that means this instruction should be executed. We wait for some time, right? We need to store the intermediate results somewhere and then need to process the next instruction by the hardware. So it's not an easy task, as you can see. To synchronize everything is a very complex operation, isn't so? One after another, you have to do that. The machine is a dumb machine. The hardware is dumb. It does not understand anything. If you give an input to it, it will produce an output. That's it. But you have semantics associated with the binary machine code. It's not just a flat bit of strings. I mean, it's not just a flat string of bits. So it signifies certain instructions, and those instructions has to be executed one after another in synchronism. Okay, you have to wait for certain time so that the previous instruction is finished. And then only you can start processing the next instructions and so on. Right? So in computer organization, we try to understand that how this complex the synchronism would take place and how you can utilize the hardware below it, which is nothing but a dumb hardware. How do you use this hardware below it? And so that this binary machine code is executed properly, keeping the semantics, I mean, preserving the semantics and output, and so that my desired output is generated. So for the time being, let us assume that, well, okay, so I have a high-level language program. We have some understanding that, well, I have a software called compiler, which would translate into some machine level or assembly language code. The assembler would further translate into binary bits. And then I have some controller here which would analyze this binary machine code and would execute in the hardware in a perfect fashion, so that the desired output is obtained. Okay. So that we study. So let us look into the overall system hierarchy once again. So on the left, you see the bare machine or the hardware. So this is a collection of gates, as you said, right? So it is a circuits, gates, and flip-flops. But beyond that, you have the transistors, and beyond that, you have physics essentially, so that how the transistors behave and so on. You may not need to study all of them, but this shows the overall hierarchy from bottom up. So from physics to transistors to gates to register transfer level. That means now we have different kinds of register, and instead of talking in terms of gates and flip-flops, we can talk in terms of registers. We can say, okay, I have two registers X and Y. Move the content of one register X to another register Y. So that I can tell you at the higher level, instead of bothering about how many flip-flops are there in the registers, how many gates are there in the registers, and so on. All right. So that gives an overall abstraction. So as you go up, the abstraction increases. So now you have, and finally you have the microarchitecture. That means overall understanding of this bare machine in terms of the machine language or assembly language. And the software engineer, they have the task of building the system software, which may be compilers, operating system, other programming languages, and obviously beyond that you have application software, like need to think about algorithms. For example, you want to run your sorting algorithm, so you need to think of algorithms and different applications and so on. So this is this blue zone. This blue zone is the zone of the hardware, and this zone is the zone of the software engineers. And in between lies the most important layer, which is the envelope of the bare machine, and that defines the instruction set, architecture, or ISA. All right. Okay. Is this? I mean, are these characters familiar to you?
Sherlock Holmes.
Good.
Dr. Watson.
Right, Dr. Watson and Sherlock Holmes, and Sherlock Holmes, he cracked a very difficult mystery puzzle, and Watson said, well, excellent. But Sherlock said, no, it's not, there is nothing in it. It is just elementary. It follows from my deductive logic. Okay, so if you go through Sherlock Holmes' novel and stories, you would find the strong application of what is called deductive reasoning. And in logic, we have, you are already aware that we have two types of approach. One is called deductive approach, other is called inductive approach. What is deductive approach? This is essentially a top-down approach, from general to particular. So when you write a recursive program, say for example, when you write a recursive routine, it's nothing but a top-down or deductive approach, from general to particular. And the bottom-up approach is inductive, in the sense that from particular instance to generality. So this top-down and bottom-up, the same views can be found in the domain of computer organization also. So now we are addressing the issue of what is called the computer organization and architecture. So here, as you can see, this is the strong gentleman, which represents the hardware, the all hardware resources. And once the hardware is designed, it supports an instruction set. So this is the platform of instruction set on which, standing on which the software engineers are playing. And they are writing their programs and so on. So computer organization is nothing but a bottom-up view, the actual implementation of components in hardware. Whereas computer architecture is the top-down view, the view of the computer as perceived by the software designer. So as a software designer, when you see this machine, you are not bothered about how many circuits are there, or how many logic gates are there, what kind of gates are there, how many flip-flops are there. You are not bothered about that. What you are bothered about, you need to worry about only the instruction set. Because if you know the target in the assembly language set of the target machine, you can design your compiler. Isn't so? So you are concerned with the instruction set architecture alone. That means the behavior of the machine as perceived by the software engineer. Computer architecture means this one. It's nothing but the top-down view, the view of the computer system as perceived by software engineers. In other words, the overall perspective of the machine in terms of the machine language, in terms of the collective machine language, and how those machine language has been implemented inside the hardware. That is the concern of the computer organization, or the bottom-up view, the actual implementation of components in hardware. And needless to say, this instruction set architecture, which refers to a very fundamental and important layer, lies at the interface. Okay. So now, yes. Okay. So you may imagine this way also. The computer organization is nothing but refers to the anatomy or the structural view of the machine. So suppose you have a human body. So if you are concerned with the anatomy, where is liver, heart, kidney, and etc. So then this is analogous to computer organization, or the structural view of the machine. And what would be computer architecture then? In terms of a human being?
The actions that the human can perform.
Yes, kind of personality of the machine. Computer architecture is the personality of the machine, or the what action the machine can perform, behavioral view. So organization refers to structural view, architecture refers to the behavioral view. So when you refer to behavioral view, it means the behavior of the set of machine language instructions. So this slide clarifies everything, the difference between computer architecture and organization and their interdependence. And in the middle, you have this instruction set architecture. So in summary, computer architecture is visible to the programmer. Okay, is visible to programmers only. So, and you are concerned with, as a programmer, as a high-level language programmer or assembly language programmer, see, you are concerned with what? You are concerned with what instruction sets are available in the machine. How many registers are available? What is the data representation or addressing mode? What is the I/O mechanism? What sort of memory architecture we have, and so on. So these are the parameters which are of importance to a computer architect or a programmer. So this is visible to architecture is visible to software engineers. On the other hand, organization is visible to hardware designer. So how the instruction would be actually implemented in hardware? How many registers should be there? What is the program counter? How the arithmetic and logical units should be built? How do you design the control logic or internal state? How do you implement pipelining hardware? What are the details implementation of cache, main memory, and so on? So that means the structural view, those parameters, I mean, those issues are of importance to the hardware designer. So they are of interest to, they are of, I mean, in computer organization, would be interested in knowing more about this. All right. Now you please tell me in CS today, in computer science today, which subjects are most sought for? All the students they're crazy for taking those type of courses, which are of high demand nowadays everywhere.
Machine learning.
Correct.
Algorithms.
Right. Machine learning, artificial intelligence, and data science. Okay. But in order to execute machine learning, you need a powerful machine, isn't so? In order to run artificial intelligence algorithm or data science, you need an intelligent machine, isn't so? So when you study machine learning, artificial intelligence, and data science, don't forget the machine below it, which is supported on two fundamental pillars, computer organization and architecture. And in this course, we try to understand the details of and what are the issues in designing computer organization and architecture. All right. Now let us talk about this computer design approach. One possibility is that you build the hardware first. That means you start with computer organization. So maybe you start with an adder, then you design a multiplier, and then you design some flip-flops and design some registers. Keep on interconnecting them one after another, starting from a small machine, keep on building bigger and bigger machines and so on. So you start from computer organization, and once you finish designing your machine, and then you declare, okay, I have designed this machine, and this machine would support this sort of instruction set, or ISA, instruction set architecture. And once the instruction set architecture is declared, you can design the overall software and so on. So on the left, well, so on the left, you see that this is what is called a bottom-up approach. That means you design the hardware first, and once you design the hardware, it defines the instruction set architecture. So that's one approach. But you would realize that when you were talking about billions of transistors, this kind of approach would fail. So what you need to do is to start from instruction set architecture. That means what is expected from the architectural point of view. I mean, what kind of instruction set or power of instructions is required by today's software engineers. So that's why you start from instruction set architecture and then design the computer organization below it. So this is called top-down approach. ISA first, hardware later. And once the instruction set architecture is done, then you can keep on developing system software, OS compilers, and so on. So the modern approach is, start from instruction setup architecture. So this is the starting point. So remember, I told you that where to start from. So this is the place where you should start from in designing a very large machine. You start from instruction set architecture. Think of your architecture and instruction set first. That you want a machine which would be able to support this kind of instructions, and then ask the hardware engineers that I need this kind of architecture. You please design the computer organization, the hardware below it. And given this instruction set, you may tell the software engineer, well, my machine supports this kind of instruction set architecture. Now you keep on building up your software based on using this instruction set and so on. So we take the middle path. So the middle layer is the starting point. All right. So that is the overall lesson of computer architecture organization. So in instruction set architecture is the set of assembly language instruction that separates the interface between the hardware and software. So in top-down design, we start from the instruction set architecture, and then the appropriate hardware platform is built to support it. Based on the instruction set architecture, the software engineers, then they can develop the upper layer softwares, and accordingly you may go further up. And once the ISA or instruction set architecture is fixed, and this is an important issue, once the instruction set is fixed, then software and hardware engineers, they can work independently, right? The hardware engineers would work independently to implement that instruction set. The software engineer would assume that that instruction set would be available and keep on working, building up their software. So the hardware engineer and software engineer, they can work independently. You can start from the middle. So very important issue, And ISA has to be designed in such a way so that it optimizes the performance supported by the available hardware technology. So this is the concept of instruction set architecture. Basically, it's nothing but common sense. As you can see, we'll see that in computer organization architecture, most of the notions are based on common sense. So what is inside the hardware? Just 5 easy pieces. So you have, this is called the central processing unit or the processor. So in the processor, what would you have? You have a controller, first of all, which will take care of the sequencing. You need registers that would hold the intermediate data. You need arithmetic logic unit to perform arithmetic, because the basis of computation, all computation reduces to arithmetic operations finally. Isn't so? Any computation finally reduces to arithmetic operation. Addition, subtraction, multiplication, difference, nothing else. So you need a very powerful arithmetic and efficient arithmetic logic unit. You need a controller. This is a finite state machine, which takes care of controlling everything. You have registers, and of course you have memory. And obviously you need this input-output devices in order to communicate with the system. So this part is called the central processing unit. And to start with, we just notice that the hardware is nothing but it comprises 5 easy pieces: control, arithmetic logic unit, memory, input-output, and data path. Right? This yellow line, these blue lines. Nothing else. So in computer organization, we would see this, how these components, the control, arithmetic logic unit, memory, input, output, data paths can be designed, and how they can be interconnected in such a way so that everything, and these billions of transistors would work very nicely in a synchronous way. Now this is a very important diagram. It shows 3 things, that when you talk about digital system design, or in other words, a processor design, for example, in particular a processor design, you can view the design process from 3 perspectives. And these 3 perspectives, one is called the behavioral domain, other is called the structural domain, and other is called the physical domain. And you see some concentric circles. And this circle means, look at this circle here. So here, this node is logic, this is gate, and this is cell layout. So the entities which lie on the same circle, it means that they are the same thing. They represent the same thing, the same concept, but at different abstraction level. Like when I say logic design, when I say Boolean algebra or logic, you can so this is a behavioral abstraction. That logic can be implemented using interconnection of gates from a structural point of view, isn't so? And when you talk about the silicon chip, you don't see AND gates or gates. What you see is the collection of some transistors, some cells, something like that. So these are the 3 equivalent view, the behavioral view, structural view, and the physical view. And the circle denotes this equivalence. So at the bottommost level, for example, you have transistors structurally. That means when you are talking about components, you have transistors. But when you talk about implementation, how the transistor is implemented on a silicon chip, you have different layouts. You have diffusion layer, polysilicon layers. You have layers one after another. So those layers can be thought of as just different shaped rectangles or deposition of different materials, right? So from the physical perspective, it is nothing but some sort of layouts, geometry of layouts. On the other hand, from the behavioral perspective, the transistor behavior means what? Some kind of transfer function. That means voltage current equations, differential equations, and so on. That's similar things like that. Like you have logic. Logic can be implemented nothing but this interconnection of gates. Gates are nothing but interconnection of cells and so on. All right. So you have the register transfer in the behavioral domain. Register transfer the content of one register from another register. Move the content of one register from another register. Now, in terms of structure, you have these flip-flops and so on. And in terms of layout, you have different modules at the geometrical level. So you have the same thing, but represented from different perspectives. And these concentric circles, they denote equivalence. All right? Are you with me?
Yes.
And this is the famous Gudsky-Kuhn Y chart, very old, 1983. And these three directions, behavioral domain, structural domain, and physical domain, they refer to three subjects or three topics. So could you please tell me what would be these topics? Structural domain, behavioral domain, and physical domain. I mean, these domains are studied as three different topics in computer science.
The behavioral domain will be computer architecture.
Yeah, correct.
You
Structural domain is computer organization. You already talked about that, right? Processor, ALU, gates, transistor, because the hardware components. Behavioral domain, you are correct. That defines the computer architecture. And what will be the physical domain?
Switching circuits and logic design.
Huh?
Switching circuits and logic design, or
yeah, sort of.
Introduction to electrical engineering.
Right, more of VLSI design. How the chips are actually designed. Because now we are talking about cell layouts, floor plans, physical, because the entire circuit has to be implemented on the chip, right? So that is studied in our VLSI design subject. Essentially, this slide is very important. It correlates apparently three different concepts, but they are actually interconnected, as you can see. From the structural domain, you have computer organization. From the behavioral domain, you have computer architecture. From the physical domain, VLSI design. So they are equivalent concepts. So everything is interconnected. So now, this is I have listed some factors which resulted the exponential growth, the technology scaling of computing paradigms. Why do we experience this kind of technology scaling? Obviously, one thing is evolution of computer architecture. New concepts are coming up. Growth of semiconductor technology and the IC design fabrication process. Memory technology has advanced significantly. Algorithms and data structure, they play a very important role. Programming languages, development in compilers and OS. Test verification error management techniques. Imagine that you have billions of transistors, so you need mechanism to ascertain whether the circuit has been designed correctly. So you need verifications, and the circuit should function correctly. You need testing and so on, fault tolerance and error management. And bootstrapping, we talked about that. Use the power of present computers to design the complexities of next generations, to handle the complexities of next generation of computers. Design automation using bootstrapping. And parallel and distributed computing, obviously network, cloud, and Internet of Things, and so on. So these are the factors which are responsible for the exponential growth of this computing paradigm, which you are now experiencing nowadays. All right. Okay, so this is my last slide today. So we are talking about evolution of computer design and so on, everything. 50 years of history. So let me ask you, are you familiar with what was the, can anybody tell me which one is the first computer built in India? Indigenously. Anybody heard any stories about that? No? All right. So it happened in around 1966, you know. It's a fully transistorized digital computer named ISI-JU, was designed and commissioned with joint collaboration between Indian Statistical Institute, ISI Kolkata, and Jadavpur University. That's why it is called ISI-JU. This is fully transistorized, meaning that there was no vacuum tube and fully digital. And it was named as ISI-JU, you know. But nobody remembers this, you know. And this is the picture which shows the front end of the machine, you know. So this is the control room. So during that time, you do not have the monitor and so on. The monitor technology has not yet come. So you had some switches and so on. Okay. And even before that, so this is a digital computer, but even before that, in 1953, S.K. Mitra, Shamarendra Kumar Mitra, he designed and constructed the first analog computer built in India for solving linear equations with 10 variables and related problems. So you know what an analog computer is? It's a computer which is built with operational amplifiers and so on. So it's an electrical circuit which can immediately solve an integration or differentiation. I mean, it's not digital, it's purely based on analog circuits. You know, those are called analog computer. You know. And nowadays, you know, again, analog computers is in the offing because the speed of analog computer is fantastic. But imagine that it's amazing that in 1953, so many years ago, more than 70 years ago, this gentleman constructed the first analog computer built in India for solving linear equations with 10 variables and other related problems. You know. And during the Indo-China War in 1962, so the government of India, the army, they wanted to solve some differential equations to study the trajectory of missiles. And so they entrusted Indian Statistical Institute to take care of this. And the same analog computer was used for that purpose. Interestingly, if you visit Mountain View, California, there is a museum which is known as the Computer History Museum. It is in California, and the town where the Google headquarters is located. Isn't so? So if you visit this museum, you would find this plaque. You know, so it reads in memory of Shamarendra Kumar Mitra, this gentleman, who designed and built India's first computer at ISI Kolkata in 1954. So if someday you get an opportunity to visit this museum in the US, and if you have some time, please go to this place and you would see this plaque. You know. Okay, thank you very much for today. Any questions?
Sir.
So let me say goodbye today, and I'd see you tomorrow.